Okay, hello everyone. So we are starting a new topic today, that's electric field. And under electric field, we'll be talking about. We'll do some calculations, continuous charge distributions. That's for university physics only. That the continuous charge distributions. We talk about field lines in general. Motion of a charged particle in an electric field, and then maybe we'll go over some conceptual stuff like how this idea of electric forces and electric field applies in biological topics, right? Alright, so what is electric field? Now we know that we talked about this in the previous discussion, that if there's two charges, it can be two or more, but let's say two charges, positive and a negative charge, there is a force between them, and we know that it's an attractive force, and we know how to find it, the magnitude. If the two charges are Q1 and Q2, we say that force is equals to K times Q1 Q2 over distance squared. So the distance here, this R distance, is the center to center distance. Now we know how to calculate the magnitude. So a big question that early scientists, early researchers had was, okay, they figured out that there is a force between charges. They figured out a way to calculate it, but they were not able to explain why there is a force, why one charge, or how one charge can exert a force on another charge. Because the force everybody was used to, it's like contact forces. For an example, let's say you have a box here and you want to move it. If you want to apply a force and move it, you have to be in contact with it, right? So you're applying a force like this. There's a physical contact between the object and the force. But in this case of two charges, they have some separation between them. They are not physically next to each other. They can be million miles away. But still, one feels a force due to the other one. This issue is common in gravity also. The force between planets. These were early questions researchers and scientists had. How do things apply force on each other if they are not in physical contact with each other? So to explain that, they came up with the idea of electric field. So what is electric field? So it is something like this. It's conceptually. Let's say we have a charge. Let's say charge Q, a positive charge. We say that this charge is creating an electric field around it, right? It's everywhere, it's around the charge, and it has properties like close to the charge, it's pretty strong. So I'm going to make it look darker. As you go further away from it, the field strength decreases. So we are assigning some property to the charge, saying that it creates an electric field, it's around the charge, and as you go further away from it, the strength decreases. So the better way to represent this electric field is, here's the point charge. So let's stay with the circular one first, a spherical charge, and we say that there's electric field. We use something called electric field lines going away from this. And the field near to the charge is stronger. As you go away from it, the field strength decreases. These are called electric field lines. and electric field is denoted by capital letter E. And we can say that it's proportional to the distance, inversely proportional to the distance, 1 over r squared. That means when r is smaller, means right close, like over here, if you measure a point here, it has some distance. To a point here, if you measure it, it has a bigger r. When r gets bigger, E becomes smaller. If r is small, E becomes bigger. So that's an inverse relationship, right? Closer to the object, there's more electric field. You go further away from it, electric field decreases. Now, we represent electric field using these arrows. For a positive charge, we say that the electric field extends outwards, so these arrows are pointing outwards. For a negative charge, let's say an electron, electric field is coming into the charge, so we draw the field lines pointing inwards. The rest is same. Closer you get, closer to the charge, stronger the field. Further away from the charge, it gets weaker. This is a simple case. It's a spherical charge, so the electric field around it, around this charge is also symmetric. It's a spherical, it's like a sphere extending outwards, represented by the field lines, and this is how they behave. Alright, so let's open a new page and talk a little bit more about this. Okay, so now you have an idea what an electric field is. So it is a force field. It's a field created by a charge or by a bunch of charges. Okay, so once again, let's say we have a proton or a positive charge. So it creates this field around it. If it is a spherical charge, the field is going to be symmetric. Now, if you bring a second charge, we are trying to understand how there's force between two charges, right? Positive and negative, we know that there's an attraction. So if you bring a second charge to the vicinity of this first charge, now I'm bringing an electron and I'm going to place it here. Now this electron, it is in the field of this positive charge, right? This positive charge is extending in all directions. This electron is surrounded by the electric field of the first guy. So now the electric field is in touch with this electron. That creates a force on it and it makes an attractive force. Okay, so the first, if you think about two charges, right? Let's say this is Q1 and this is Q2. If you want to find the force on Q2, right? If you want to find the force on Q2, we look for the field created by Q1. So Q1, let's say it's a positive charge, it's creating an outward electric field like this. So Q2 is in that electric field made by the first guy and it feels a force. Now you can look at the reverse of this. So you have two charges Q1 and Q2. You want to find the force on Q1. So we should look for what kind of field Q2 is creating. So Q2, let's say this is a negative charge. So it creates an electric field pointing towards it. This is the E field of Q2. So let's call it E2. Let's call this E1. So Q2 is creating an electric field around it. Q1 feels that field. It is in the vicinity of that electric field. So Q1 is feeling a force. So this is how we explain the Coulomb force, or force due to electric charges. We say that there's an electric field. You bring a charge and place that charge in that electric field. The charge feels a force. And you can, there's another equation to calculate the force. The advantage, why do we need electric fields? Why can't we just use the Coulomb equation all the time? The advantage is we don't have to worry about a second charge. If all we need is a force acting on a given charge, we don't need to worry about who's creating the electric field for it, right? We just need to know the electric field. So in other words, I can say, here's an area, this area in space. There's an electric field. Here's the electric field. So this time I'm drawing it like parallel lines. Here's an electric field. Here I am placing a charge in this electric field. Find the force. So there will be a force acting on this charge. Find the force. So in this case, here's a very important thing to remember. If it is a positive charge, the force is in the same direction as the field. And this is the E field. Force is also F also in the same direction. If I place a negative charge, the force will be in the opposite direction to the electric field. That's the advantage. In Coulomb equation, to find the force, if you want to find the force on this guy, we need to know whether there's any charges around it. Like, okay, so if there's a negative charge here, we know that it creates a force this way. If there's a positive charge here, so it's going to add another force on this way. So we have to find the sum of the forces, right? So if you have multiple forces around this, multiple charges around it, it's going to add multiple forces. But if we know, so same diagram again, if we know what the electric field, all these guys together, is creating at this area, then when I place a charge in it, I can easily figure out what the force is. Okay, so electric field is convenient that way. If you know that, finding the force is much easier. Why do we talk about electric field in detail? In advanced studies, when it comes to like, could be biological or chemistry kind of medical research, electric fields are really important. Behavior of molecules, atoms, anything that has a charge is determined by what kind of electric field around them. We use electric fields a lot in medical imaging kind of fields. We use the knowledge of electric fields to so many medical devices like EKG, ECG, all those diagnostic devices. Electric field is a main function. So having that understanding will be important when you go into these higher studies or research and industry. So this is a fundamental and an important thing. Okay, let me erase this and let's talk a little bit more about this. Okay, so we know that an electric field, so denoted by E, it's a vector, so we can put a little arrow to indicate that it's a vector. Electric fields are denoted by graphically can be drawn by lines with an arrow. So if I draw an arrow like this means there's an electric field pointing to the right, or we can say there's an electric field pointing up or north, right? So let's say there's an area where there's an electric field pointing to the right, so I can draw a bunch of lines parallel. This means this is a parallel electric field. Field lines are parallel. It's a uniform parallel electric field. Mostly these kind of fields are created by like a group of charges. For an example, if I take a metal plate or a piece of metal or some rectangular object and place a lot of positive charges evenly on it, this thing can create a parallel electric field. If I have a spherical object and place charges on it, maybe positive, it creates a charge that is extending radially outwards. So depending on the shape of the electric field, we can kind of assume, kind of guess what the shape of the object is. Or if you know the shape of the object, the source of the charge, we can figure out what the shape of the field can be. So, and or we can just draw one line and say this is the electric field. And when you place a charge in this electric field, let's say you have this charge Q, there's a force acting on it. If Q is positive, force is in the same direction as the field. Is the field. If the charge is a negative charge, force will be in the opposite direction. Okay, so we know that how to figure out the direction of the force. Now we can relate this to our previous examples, force between two charges. Here we have a positive charge, here's a negative charge. We know the force is towards each other. Let's say this is charge 1, charge 2, this is F12, this is F21. Alright, so now let's think about it in terms of electric fields. Here we have Q1, which is a positive charge. Electric field is outwards. I'm going to place this negative charge here, Q2. At this point right here where the charge is, E field is to the right, therefore force has to be to the left. That's what we need, right? Between opposite charges there has to be an attractive force. I have the positive charge, here's the electric field around it. I place a positive charge here, plus Q. At this point, electric field is pointing this way. The force has to be in the same direction because this is a positive charge. It takes the same direction as the electric field. Now if you go back and think in terms of Coulomb, positive and another positive, it's a repulsion, so force is outwards. Okay, so you see that we're talking about the same thing but in a little different way. Now, how do we make measurements? Now let me go to the next slide. How do we define the electric field? Electric field is defined as the force on a small charge or force on a charge divided by the magnitude of the charge. Okay, so what does that mean? Let me erase this one more time. Electric field is given by force divided by the charge. Okay, so let's say here we have an electric field. We place a charge in this electric field. So here's the charge we place and the value of this charge is Q. It exerts, the electric field is creating a force on it, F. If we measure this force, right, we measure this, we know this, we know the force, we know the charge. Electric field is equals to force divided by charge, or you can say force per unit charge. That gives us the unit for the electric field. Force is in newtons, charge is in coulombs, so the units of electric field is newtons per coulombs. Right? That's the SI unit. Alright, so let's try a simple example. Here we have an electric field. We don't know what the value is, right? We have no idea. When we place a charge on this electric field, we're placing a charge of 5 microcoulombs. We see that, let's say it's a positive charge, so the force has to be in the same direction. When we place the charge, we see that there's a force of 10 newtons acting on the charge in the same direction. So what is the electric field? Electric field is force divided by charge. 10 newtons divided by 5 microcoulombs. So 10 divided by 5, actually this can be written as 10 over 5 times 10 to the negative 6, right, coulombs. This is newtons. So we have 2 times 10 to the 6, this negative becomes positive, 2 times 10 to the 6 newtons per coulomb as the electric field. Yep, here you have the answer. Let's try another example. Let me erase this. This time it says we have a positive charge equals, let me make up some problem, 2 microcoulombs. When you place this charge in an electric field, there is a force. There's a force acting on this charge. Force is, let's say, 6 newtons to the left. So here we have a charge, 2 microcoulombs, positive 2 microcoulombs. We place this in an electric field. So over here there's an electric field. We don't know anything about it. We don't know the magnitude, we don't know the direction. But we see that when you place it, there's a force of 6 newtons to the left. So the force is to the left, 6 newtons. Question is, what is the electric field? We know that whatever it is, electric field takes the same direction. The force for a positive charge, force and electric field should be in the same direction. So this is a positive charge. If the force is to the left, electric field has to be to the left. So here's the electric field pointing to the left. What's the magnitude? It's force divided by the charge. So that will be 6 newtons divided by 2 times 10 to the negative 6 coulombs. We have 3 times 10 to the 6 newtons per coulomb going to the left. Okay, here's another one. We have a negative charge equals, let's do the same thing, 2 microcoulombs. You place it in an electric field. There is a force of 6 newtons to the north, or going up. So this is a negative charge. Okay, so here's the charge, negative 2 microcoulombs. There's a force when you place it in this electric field. So there's an electric field around it, not created by the charge, right? We are not talking about the electric field of its own. It's always the electric field is external. Somebody else has already created this electric field. We bring this negative 2 microcoulomb charge. Okay, so it's important to remember the field we are talking about is always external, not its own electric field. So here's an electric field. There's a force of 6 newtons going up, going to the north. What is the electric field? So think about it. For a positive charge, field and force same direction. For a negative charge, field and force opposite direction. So the electric field has to be pointing downwards. In this case, the field is downwards. And what's the magnitude? E is force divided by charge. So 6 divided by charge. In this case, you don't have to put negative. It's okay to put that. If you put negative 2, you get negative 3 and 10 to the negative 6. Negative 3 times 10 to the 6 newtons per coulomb. This negative sign tells you the electric field is opposite to the force. That means if force going up, electric field has to be pointing downwards. even if you don't use the negative sign, even if you just do this, 6 over 2 times 10 to the negative 6, you get 3 times 10 to the 6. With this, you have to clearly explain which way the electric field is pointing. In this case, you have to say that it's going in the downward direction. Okay. Okay, so let's think about another example. This time, what is the force, this third question, what is the force exerted by an electric field of 3 E negative 5? So E field is 3 times E negative 5, that means 3 times 10 to the negative 5 newtons per coulomb. So this is a very, very weak electric field. Let me change the number, right? Let's just say plus. Okay, I'm changing the question. Okay, so the electric field is this. What is the force exerted by this field on a charge of 2 microcoulombs? What's the force? So E is force over Q, therefore force is EQ. We multiply it to the other side. So electric field 3 times 10 to the 5, charge 2 times 10 to the negative 6, 6 times 10 to the negative 1 newtons, or 0.6 newtons. So it's a positive charge. If field is going up, the force will be also pointing up because it's a positive charge. Do the same thing for a negative 2 microcoulomb. E is F is EQ. Electric field is 3 times 10 to the 5 times negative 2 times 10 to the negative 6. It's 2 microcoulombs negative. You get a negative answer. Same thing, 0.6 newtons per coulomb. Newtons, which is negative. We know that it's a negative charge, therefore the force should be pointing against the electric field. That's the same thing this negative sign tells you, right? If it is a negative charge, the force and electric field has to be opposite. Okay, so now we have an idea. If the electric field is given, we know how to find the force acting on a given charge. So the most important thing about the electric field is it's always an external electric field. Somebody else had already created this. Some other charge or a group of charges creates this electric field. You bring a charge from outside, place it in that, and then you calculate how much force it's feeling, right? Electric field is not its own electric field. You bring a charge, it has its own electric field. It can apply force on somebody else, not on itself. Okay, so a charge feels a force due to an outside electric field. Alright, let's move on. So we discussed that there are electric fields, charges can create electric fields, and when you bring some other charge into that electric field, they feel force. So, and it's denoted by this, and if you know the force on something, and if you know the charge of that thing, the electric field around it can be calculated by F over Q. Or if you know the electric field and what the charge in that electric field, you can calculate the force acting on it by EQ. Now, so all these times I gave you the electric field. For an example, I told you, okay, E field at this point is 2 times 10 to the 6 newtons per coulomb. Now, let's think about how to create this. With positive charges, we can create positive electric fields. Negative charges, we can create negative electric fields. If we have a single spherical positive charge, it creates a field extending outwards. you have a negative charge, it creates a field pointing towards it. If you have a positive line of charges, it creates a very parallel electric field extending outwards. Right, there's extending outwards here also, but compared to the sides, the edges will be smaller. If you have a negative line of charge, like you take like a conducting wire and put bunch of electrons on it, it will create an electric field like this, going into it. You can have a area, like a metal sheet, like a rectangular piece of metal, and put some bunch of charges. It will create an area of parallel electric field. Now, these things have so many nice applications. We will talk about this later. A lot of devices, measuring equipment, imaging equipment, digital, so many things, right? So we will get to all these things later. But so if you have a charge distribution, or if you have a single charge, how do you find the electric field creates by it? What's the strength, what it looks like? So let's talk about that. Let's start with the most simplest case. Let's start with a point charge. Okay, so let me erase this. Electric field created by a point charge. Let's take a positive charge, and let's call this charge is Q. Or we can go with just little q, that's fine. Okay, so we know that because it's positive, the electric field is radially outwards. If we plot how field changes with distance, right, this distance, so let's say I'm measuring the electric field at this point R1, this point R2, this point R3, like that. So distance is increasing. I see that there's the biggest electric field here, getting smaller and getting smaller and smaller. So if you plot the strength of the electric field with the distance, what you get is something like this. It's exponentially decreasing. As you go to infinity, it becomes zero. It reaches zero. Alright, what's the equation describes this? It's kind of similar to the Coulomb equation, which is K Q1 Q2 over R squared. The difference is here we have only one charge. We're trying to find the electric field created by this single charge. You bring a second one into the vicinity of this, we can find the force acting on it. But to find the electric field, we just need one charge, and the equation is given by KQ over R squared. You see that it kind of have the same look as the Coulomb equation. The only difference is it's only one charge. This is the guy who's creating this electric field. So the Coulomb constant times the charge divided by distance squared. So if I want to find the electric field at this point E1, I put R1 value here. If I want to find the electric field E2 at this point R2, I put R2 here. Likewise, by changing the distance, I can find the electric field at each point, and it's decreasing with the distance. Same equation goes for a negative charge. The difference is it's pointing towards the charge. Okay, so let me show you the slide for that. So this again tells you that here's an electric field, positive charge, field and force same direction, negative charge, field and force in opposite directions. Electric field surrounds every charge. This slide should have come a little earlier. Anyways, okay, for a point charge, electric field is KQ over R squared. Also, I think I kind of mentioned this the other day. E equals KQ over R squared. the force equation, if you have two charges, Q1, Q2, we write force equals K Q1, Q2 over R squared. This constant K, which is Coulomb constant, so right here, 9 times 10 to the 9. This is not a fundamental constant. It has more stuff in it. So there's another way of writing that. We can write K as 1 over 4 pi epsilon naught. Now epsilon naught is a more fundamental constant. This is called permittivity of the space or of the medium. Permittivity of space. What does that mean? So I can write this equation, E equals 1 over 4 pi epsilon naught instead of K, Q over R squared. Same thing. I can write this one the same way. Instead of K, I can write this 1 over 4 pi epsilon naught. This is more basic because it has this basic constant called the permittivity of the space. It tells you, like, if you have a charge, how much this particular region around it, the space around it, permitting this electric field lines to travel through it. Free space means our atmosphere, like empty space, is the best. Highest permittivity, electric field lines can pass without any obstructions. Our atmosphere, that's not really free space, it has gases in it, but still it's not that bad, it's good. Certain materials, certain mediums won't allow electricity to pass, electric fields to pass through them, so these things won't create much electric field. They won't have a lot of force between the charges if the permittivity is high. Okay, so that's the idea of this. The value of this number epsilon naught for free space, means the space without anything, like a good vacuum, is 8.85 times 10 to the negative 12. We will use this format later when we go to other topics, which is more useful than sticking with K, right? This has more applications. In many calculations, this 4 pi term cancels out. That's the advantage. Yeah, so that's the idea. If it is a point charge, this is how we calculate the electric field. Okay, so let's try an example real quick. All right. Okay, the example question: electric field of a single point charge. Calculate the magnitude and direction of the electric field at a point P, which is 30 centimeters from to the right of a point charge Q equals this. So here we have a point charge where Q, the charge, is 2 times 10 to the negative 6 coulombs. We want to find the electric field at a point 30 centimeters to the right. This point here, this is point P. 30 cm from the charge, away from the charge. The question is, what's the electric field at this point? Alright, this is a point charge. Point charge means, again, it's a spherical charge. We know that, and it is positive. So the electric field at this point must be pointing outwards. We need to find the value. It's given by KQ over R squared, 9 times 10 to the 9, 2 times 10 to the negative 6, 30 centimeters, 0.3 squared. Okay, so do the math and to figure it out. You might see some answers in the bottom under the slides, those answers could be incorrect, so don't go with them. Question could be different. I sometimes change the questions. So we'll do the math and see what we have. Okay. So I have 2 times 10 to the 3 over 100. So 2000 over 100 20 newtons per coulomb in this direction. So this is what I have. Okay. All right. So go ahead and repeat the question for a negative charge and see what the electric field is. It should be pointing in the other direction. Another things, example problems we can think about. What if we have 2 charges? Let's say here's a positive charge and here's another positive charge, separated by some distance. Let's say they are equal. This is 2 microcoulomb, this is also 2 microcoulomb. What's the electric field at the midpoint between them? So how do you find this? You can calculate the electric field E1 due to this guy, if you know the distance, E2 due to this guy, and then the vectors, you add them together to figure out what the resulting electric field is. So I can put positive and negative. I can ask the electric field right at the midpoint, some point here, or some point over here. So we find the electric field this way, find the electric field this way, take the components. So many interesting things. I know you guys are not thrilled about it, but there's so many different things you can do with this. All right, so let's stop here because it's already 40 plus minutes. I like to keep the videos around 30 to 40 minutes. I'll post some questions soon so that you can work on those. Okay then, thank you everyone.